Welcome to Ready to Derive. In this video, we're going to be discussing relations and functions. Some of the topics that we're getting into are genes and vending machines. You might wonder what that has to do with relations and functions, and if you want to find out, you've got to stay tuned. We're going to get into definitions and some terminology associated with relations and functions, talk about domain and range, really explore the coordinate plane, which is where relations and functions reside in mathematics most of the time. And then we're going to address the vertical line test. So without further ado, let's begin. So let's begin by understanding what a relation is in mathematics. And to do so, we need to know what an ordered pair is. As the name indicates, an ordered pair is a pair of objects that could be numbers, objects, letters, things, in which order matters. And I found an example of an ordered pair in the real world, and we're looking at the dimensions of a pair of genes. So we see that these genes, the size are 29 by 32. That X is not multiplication, it indicates by. So 29 by 32. In the same way that if you bought a piece of furniture like a desk or something, they would give you the length times the width times the height so that you knew the dimensions. So the order matters and they represent things. So what does the 29 refer to? This refers to the waist of the genes in inches, and the 32 refers to the length, or technically the inseam, but the length in inches. So in mathematics, we write an ordered pair with parentheses and a comma like that, 29, 32. And we need to understand that we must specify what the first element of this ordered pair represents and what the second. So a relation is just a set of ordered pairs that share some characteristic. So imagine if I took a bunch of genes, a pair of genes, several pairs of genes, and went into the changing room. So here are the gene sizes I brought into the changing room. This is a relation. There's nothing special about this relationship. You know, other relations can have a lot more in common, but this share the characteristic that I brought them into the changing room. A set we usually indicate with curly brackets, and we separate the ordered pairs with commas. So we need some terminology that goes with relations. So we need to understand what the domain of a relation is. It's the set of all first elements. So let me just use a different color here. So the first elements, we have the waist sizes, in other words, 29, 29, 30, 31, 32. So when we write the domain, we write it like this, we just list the elements. So I don't need to write 29 twice because that's obvious. And here are the waist sizes. That's the domain of this relation. And the range is all of the second elements or outputs. So that would be the 32, 34. Oh, there's only two elements in the range. So 32, 34. And usually we can represent the domain range with what's called a mapping diagram. And it looks like this. So we put the elements of the domain in here. So we'll put 29, 30, 31, 32. And then we do the same for the range. So we put, let's see, we have 32 and 34. And then we just basically draw some arrows connecting them. So 29, so the 29 goes with the 32, and the 29 also pairs with the 34. The 30 pairs with the 34. The 31 pairs with the 32, and the 32 with the 34. And I know this looks a little confusing, but it will help us in establishing what a function is. So let's define a function now. So a function is a very special type of relation for which each element of its domain has only one corresponding element in its range. We can say this more simply by exchanging domain and range with input and output. So each input corresponds to exactly one output. Now let's just recall, so a relation, we know that it's a set of ordered pairs. And for the ordered pairs, we can call the first element, we refer to it as the input, and the second, the output. So in the example we were just looking at with the genes we took into the changing room, let's call up the set of the relation here. And if we notice, if we look closely, we have a little problem here because we have the input of 29 inches of waist corresponding to, in this pair, 32 inches length. But then we also brought a pair in with the same waist, but with a different length. So that violates what it needs to be, a function. Let's look at this in the mapping diagram. How does this show up in the mapping diagram? We see that 29 corresponds to 32 and also 34, which is a problem. Notice it's not a problem that 3 different waist sizes, 32, 30, and 29, all correspond to 34. That's not an issue. What is an issue is this arrow here, and these can't both coexist and give us a function. So how could we turn this relation into a function? We just have to get rid of the culprit, one of these 29. So if we got rid of that pair, we have now a function. Notice that none of the inputs, none of the wastes are repeated. See, every waist size corresponds to a different length. And if we look at the mapping diagram, what's changed? The only thing that's changed is that we got rid of this arrow here. So 29 is not confused about who it goes to. 29 corresponds to 34, and so does 30, and so does 32, but that doesn't matter. It's still a function. So one important observation here is that all functions are relations, but not all relations are functions. So let's do a little practice of identifying if a relation is a function. We're going to look at 2 real-world cases. So here is one scenario. For my students in my AP Calc class, I was very interested in what their final average in the class was and their AP exam score. So I'll give you a couple of results. So somebody who had a B- in the course ended up with a 2 in the exam, not surprisingly. Someone who had a B+ ended up with a 3. Someone who had, let's see, an A- ended up with a 4. I was very happy about that. But, oh wait, somebody who got an A also got a 4. Is that a problem? No, because the input is not repeated, right? So the input, an A- can give a 4, an A can give a 4. What we can't have is a repeated input. Okay, so you can predict this coming. Somebody who got an A, another student also got a 5. In fact, there's lots of repeated ones. So for example, someone who got a B+ also got a 4. So we have a lot of problems here because B+ is repeated, the A is repeated, and that automatically disqualifies it from being a function. So not a function. All right, so let's consider this scenario. At the vending machine, the set of ordered pairs, code entered, and the drink delivered. So this is a picture I took of our vending machine, just one portion of it. And we can see that, well, I'm going to do this more like a mapping diagram now, that if I type in A1, I get a blue iced tea, A2, all the way up to A5. Actually, it extended beyond this. There were kind of more. I think it went all the way up to A10. So all of those deliver blue, whereas if I type in B1, I get green, etc. B2, I won't do it, all of them. B5, that gives green, and just one, let's just pick C4. If I want to write it as an ordered pair, I got C4 delivered orange. This, as you can see, there's no repetition of the inputs, and so therefore this is a function. Yes, it's a function, right? This example, and in some ways for a vending machine, you want it to be a function, because imagine if it wasn't. Imagine if you typed in A1 and you didn't know if it was going to deliver you a blue or green iced tea. Well, it was fine if you knew that it was going to be a mystery color, but it's not so good if you know exactly what you want. So a vending machine is a perfect real-world example of why functions matter. Now we're going to transition to the coordinate world, which in mathematics is where a study of relations and functions mostly exists. So an ordered pair in the coordinate world is just our xy coordinate. So here's a relation which we'd like to investigate as to whether it's a function or not. And right now these don't have any meaning. So it's not like waist size and length of gene. These can just be points on a plane, and we are going to start by graphing them. So -3, 3, -3, 6, -1, 1, 2, 4, and 3, -2. And of course the question is this a function, yes or no? Well, you probably already saw that the -3 is repeated, so the input of -3 goes to two different outputs, and that's a problem. And you can see that problem in the graph because the 2 points are vertically aligned, so be on the lookout for that. So no, it's not a function. While we're here, let's just review domain and range. So domain, again, is the inputs, so the x values when you're in the coordinate world. So those x values in order, -3, I don't need to write that twice. We just need to list the distinct values, and our range, we go, the y values go as low as let's see, -2. So trying to put them in order, -2, 1, 3, 4, 6. So how could we make this into a function? And this time I'm going to realize that, well, one of those -3's has to go. So maybe I might just change that -3 to a -2. And if we graph that now, let's see, so -3, 3, -2, 6, -1, 1, 2, 4, 3, -2. And so first of all, notice that none of these points are aligned vertically with one another. That's a good sign. So is this a function? Yes, it is. And the domain, notice that I shifted, or the range stays the same, and notice that I shifted one of the -3's to -2, and that's my new domain and range, and this is a function. So in the coordinate world, relations and functions more often than not comprised of infinitely many ordered pairs, too numerous to list. So in those scenarios, we're going to be working with equations. So we need to learn how to graph or represent a relation or function, and we do so with the help of a table and graphing what we can of the ordered pairs. So with a table, so we have x, y, input, output, we could just take a few select values to help us get an idea for the shape. -2 squared is 4, 1, 0, 1, 4. And then we could graph those points to get an idea. So -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. Now that list I've done is a limited list. It's not all the ordered pairs. For example, I could do 2.5 and square that, and I get 6.25, which would be 2.5, 6.25. So to properly represent all the ordered pairs, you would have to connect these, right? So it's not just a discrete list of ordered pairs, it's infinitely many. And then we have to ask ourselves, is that a function, yes or no? Well, it doesn't seem like any particular x value is repeated, right? Every x value gives out one distinct y value. So we can say that that is indeed a function. And we also have a technique that we alluded to in the last slide, which is that it's the vertical line test. If a vertical line placed anywhere along the graph intersects the graph only once, then the graph represents a function. So let's take a vertical line there, let's move it along, and as we move it along, we see it's only intersecting the graph once at any point, and therefore this is indeed a function. So let's take an equation, and you can probably predict that we're trying to look for one that's not a function. Let's get those values. Let's take the same x values, -2, -1, 0, 1, 2. And when we're doing y squared equals x squared. So when x is -2, -2 squared is 4. But when we take the square root of that, we can get 2 or -2. And the same is true with -1 squared. We get 1 or -1. 0, 0 is the only combination there. But even when x is 1, we will get 1, -1. And if x is 2, well, if x is 2, 2 squared is 4. We're back up to the same situation. So we get this. So now when we try to graph these, let's see. So we have -2, 2. But we also have -2, -2. So we sense immediately that we probably have not got a function here. Here we go. And again, we've only have a partial list of ordered pairs there. So you would have to connect these like with 2 lines, and you can see that this is not a function because one x value gives out, 2 y values. So let's have a look at the vertical lines again. So this is not a function, but let's do the vertical line test to check. Okay, that intersects twice. Problematic. That intersects nearly once, but even if it was just at 0, 0, it's still all the other places that a vertical line could go intersect the graph twice, and that's a problem. So that is not a function. So we're going to end with one more practice problem. We're going to look at various relations in different forms and determine if they are functions or not. So here's a relation. Is it also a function? Well, remember, when you've got a list, rather than graphing, you can just look and make sure that none of the x values are repeated. So every x value gives only one y value out, or every input gives only one output. So yes, that is a function. What about this? Well, you can't determine until I put some numbers in there and maybe draw some arrows. But since the domain only has 2 elements and the range 4, you can probably sense that we're going to have double arrows emanating from the domain. I contrived this to be the square root function. So the fact that the domain, the element 4, pairs with 2 and -2 is a problem. Same for 1. When x is 1, so no, it's not a function. Now we have a relation in the form of an equation, and we could make a table of values, or we can sort of think carefully about this equation. So if I solve this for y, we get y equals the cube root of x. And what I want to do is just play around with a few xy values. So let's take, I know the cube root of 8, that's 2. But what about -8? Is that a problem? No, that's going to give -2. And let's see, 1 will give cube root of 1 is 1, cube root of -1 is -1 also. So unlike the square root, the cube root will give a distinct y value out. So in this case, this is indeed a function. I mean, I could graph those if it would help so that you can look at the vertical line test, but we can sense already that this is a well-defined function. And finally, we have this circle here. Is that a function, yes or no? The answer is indeed no. And for this, since we have a graph, let's just use the vertical line test. So that vertical line only intersects once. So technically, you might say, well, isn't it a function some of the time? No, because that vertical line, as you move it along, see here we intersect twice. Wherever you put it, if it intersects more than once, then the graph or the relation is not a function. Hello again, and thanks for sticking around. If you found this video helpful, please do hit the like button. And if you'd like to see more of my content, then please do subscribe to my channel, Ready to Derive. Thank you.